Hello and welcome to the Further Maths Support Programme revision recordings for Core Mathematics. We're going to be looking today at the third part of the A2 differentiation topic, and this is the third and last part. So far we've covered chain rule, product and quotient rules, exponentials and logarithms and trig functions. Today we're going to be looking at the C4 topics, implicit differentiation and parametric differentiation. You can see here that these two topics appear in Core 4 for almost all of the specifications, with MEI just touching on the implicit differentiation in C3. Okay, so let's make a start on the implicit differentiation. Now, implicit differentiation is generally considered to be a generalization of the chain rule. So if you've seen the chain rule recording already, most of the techniques that we're going to use here in implicit differentiation you will already have covered, and they should be familiar. The difference with implicit differentiation is that you're dealing with functions that are expressed what we call implicitly. Excuse me while I just get my pen colour correct. So an implicit function is one where x and y, if those are the variables that you're using, are sort of intertwined with each other. You're perhaps more familiar from earlier parts of the maths course with explicitly expressed functions. So anything which is y as a function of x is an explicitly expressed function, y on its own on one side and a function of x on the other side. We're talking about implicit functions where x and y can both appear on the same side and where they can be combined in terms within the function. So the classic example of an implicit function is a circle. Let me just give you the equation of a circle centered on, let's have it at 3, 2. Sorry, y minus 2. And let's give it a radius of 5. So if you're familiar with the equation for a circle, you can see here that we have x and y both on the same side of the equation. They're sort of scrunched up inside this square expression. This is very definitely an implicit function rather than an explicit one. It's possible to rearrange this to make y the subject of the equation and then differentiate from there. And if you were looking at this method in C2, for example, that's what you would need to do. You would need to rearrange to make y the subject and then differentiate. But by the time you get onto C3, C4, you should be able to use implicit differentiation on this type of expression. This is actually a much more useful type of differentiation technique because you can use it on any type of function, no matter how it's expressed. Okay, so the basic technique is exactly the same as for the chain rule. We're going to differentiate term by term, and where we find a composite function, we're going to differentiate by the outside function first and then multiply by the derivative of the inside function. So it's generalized up here, but this is a little bit complicated to get the hang of. It's quite hard to generalize it in algebraic terms. Much more easy to think of it as differentiate with respect to y and then multiply by dy dx. That's where your function is a function of y, as it were, but you're differentiating with respect to x. Okay, so the first term in our circle here is actually a function of x. So when we differentiate this, we treat it just as if it were any other function of x. Differentiate the outside, that gives me 2 times x plus 3 to the power of 1, and multiplied by the derivative of the bracket. Well, the derivative of the bracket here is also 1, so 2 times x plus 3 is all I need. If I differentiate this second function, again differentiate the outside function, and that gives me 2 times y minus 2 to the power of 1, and multiply by the derivative of the bracket. Now the derivative of y minus 2 with respect to x is dy by dx, because we're differentiating y here with respect to x. That just gives us dy by dx. 25 differentiated with respect to any variable is 0. And so we have our expression here, and if we wanted to, we could rearrange this to make dy by dx the subject. You can see here we have a common factor of 2, which could be cancelled away. We could rewrite this as dy by dx. Well, let's start with y minus 2. dy dx is negative x minus 3, or let's just write that as 3 minus x. So we can divide through by y minus 2 and get dy by dx is 3 minus x over y minus 2. And then if we knew a point on the circle, we could then substitute the x and y coordinates in there and get the gradient at that particular point. So let's take a little look at some questions on this. As with our previous recordings on these types of topics, there are going to be multi-choice questions all the way through. If you want to pause the recording at any point and have a little go at the question yourself, you can. I'm going to launch into the explanation, so pause, work it through, and then restart the recording, and you should find that my explanation with luck will match up with your working. Okay, so we're going to differentiate u cubed with respect to v. Now, in our example, we were dealing with x's and y's. All we're doing here is replacing u with y and v with x, or the other way around, and we're going to differentiate. So differentiating with respect to v, the function u cubed. The method then by chain rule, differentiate the outside function, that's the cube, multiplied by the derivative of the inside function, that's du by dv. Differentiating u with respect to v gives du dv, so just 3u squared du dv. And I think you can see that that matches up nicely with part A here. Let's try another one. Okay, again we've got a circle here, but this time it's expressed in the expanded form, so we can just go through and differentiate each of our terms with respect to x. So I'm just going to put the whole thing inside a bracket here and just differentiate the whole lot with respect to x. d by dx of 0. Okay, so differentiating the left hand side, the x squared term goes straight to 2x. The y squared term we have to differentiate implicitly. Differentiating the outside function gives me 2y, the inside function dy dx. The 2x simply differentiates to 2, and the minus 4y, if we differentiate minus 4 anything with respect to x, we end up with minus 4, multiplied by the derivative of y, that's dy by dx, and the derivative of 0 with respect to anything is always 0. Here we're being asked to find the gradient at the point where x equals 0 and y equals 0. Now what you could do is rearrange this expression here. We could cancel through by 2 and rearrange, make dy by dx equals some function of x and y, and then put 0, 0 in there. It's actually a little bit simpler than that, just to substitute the values straight in. So we're going to take our 0, 0 here. We know x is 0, so this part becomes 0, the first part becomes 0. The next term, when y is 0, that's also 0. We've then got our plus 2, and we've got our minus 4 dy by dx. All of that equals 0, and then rearranging that, let's just have a little second column here, that gives me 2 equals 4 dy by dx. So dy by dx is a half at that point. As I say, you could rearrange this whole expression first of all, get an expression for dy by dx generalised, and then substitute your values in, but in this case, because we're not going to use that tangent to do anything else, it's easier just to substitute the values into that raw, unprocessed equation at the top there. And if you've worked it through the same as me, hopefully you've got answer D. Okay, so now we're going to do a little bit of trig differentiation here. We've got cos y, can't resist saying cosy, equals x. We're going to find dy by dx. Now we could rearrange this and make y equal arc cos x, or inverse cos x, if that's the notation that you're used to. But the derivatives of inverse cosine of x are fiddly to do. It's much easier to stay with the implicit version, so let's differentiate both sides of that equation with respect to x. dy dx of cos x, cos y is d by dx of x. The left hand side, differentiate the outside function, that's the cosine, and you get minus sine y, and differentiate the inside function, that's the y, and you get dy by dx. And differentiating x with respect to x gives you 1, so we can rearrange here and get dy by dx is negative 1 over sine y, and I think you can see here that that matches up with answer A. Okay, the final example on the implicit differentiation then, we've got a tan and a logarithm in here. This is a good opportunity to revise differentiating logarithms. We're going to differentiate both sides of this with respect to x. You wouldn't necessarily need to write this first line in every time, I'm just doing this for completeness, just so that your notes show that we're differentiating both sides with respect to x. So when you differentiate a tan, you end up with sec squared. That's a standard that you need to know off by heart if you don't already. That's differentiated the outside function. When you differentiate the inside function, you get dy by dx. Differentiating the logarithm, those of you that were in the session where we revised exponentials and logarithms will remember that log 2x differentiates to 1 over x. If you're unconvinced about that, a little sidebar over here, log 2x is the same as log 2 plus log x. Log 2 is just a constant, so when you differentiate it disappears, and log x, d by dx of log x is 1 over x. That's one way to think of it. The alternative is to use the chain rule, d by dx of log 2x. Differentiating the log gives you 1 over 2x. Multiply by the derivative of the bracket gives you times 2, and that also leaves you with 1 over x, so we're definitely confident that that's our correct answer here. Sec squared is 1 over cosine squared, so I'm just going to rewrite it as 1 over cos squared y dy dx equals 1 over x. I think you can see then that that rearrangement dy by dx cos squared y over x, and I think that is answer C here. Okay, so we're going to take a little look at a little enrichment topic here, which is connected with the parametric equations that we're going to be looking at in just a moment. So I want you to imagine this bicycle wheel rolling along the road here, and it rolls in a little blob of paint. You can see here I've drawn a little blob of white paint on the wheel, and as the wheel turns you can imagine that the blob of white paint is going to move up, and it's going to move along the road with the wheel as the wheel's running along in a constant straight line. What I'd like to do is try to find the equation of the path that that little white dot follows. Obviously, you can imagine I would have thought that it's going to basically mark little white dots on the road as the wheel rolls around. The white dot is going to splat onto the road at various points along the road, probably each, well, you can imagine, can't you, that one circumference of the bicycle wheel is going to be the distance between consecutive dots on the road. But I'm interested actually in the whole path of the dot. Where does it go? What path does it trace out as it goes along the road? Now, if you ask people to take a guess at what that path will be, you get various different estimates. Some people think that it will make little loops like this. That's quite a good guess. Okay, so if you imagine it making loops like that, each time it touches down on the road, it's going to make a little white dot as you go along. Other possibilities, those loops might interlock with each other. Is that possible? That might be another possibility. Let's have a little look then and see how the algebra on this works out. Now, I hope you're all familiar with the idea of the equation of a circle. So the equation of a circle is going to be useful in this particular calculation. Whoops. So let's say we've got the wheel moving along at a constant speed, if you like, in this horizontal direction. I've drawn a little diagram here showing x and y axes. So I'm going to have the wheel start with its base here at the origin at 0, 0. Oops, sorry about that. And I've made the radius of the wheel equal to r. And what I've shown here is a point where the blob of paint is on the tyre, and it makes the radius joining the centre of the wheel to the blob of paint makes an angle of theta with the horizontal, and that's going to become quite important in a minute. I think we could all work out the equation of the circle. If you know that the tyre was spinning on the spot here, you know that it's spinning around this central point here, and I hope you're reasonably happy with the idea that the blob of paint sits on a circle with equation x squared plus y minus 1 squared equals r squared. Okay, I hope that makes sense to you. That's essentially because the centre of the circle is moved up a distance from the origin here. So the origin is here at O, and the centre of the circle has moved up. I'm sorry, that should be r in there, my mistake. Sorry, y minus r squared. That will move the origin of the centre of the circle up a distance r from the horizontal here. So if the blob of paint was going to stay on the circle, and the wheel was going to stay in one place but spin, this would be the equation of the path that the blob of paint would trace out. Well, that's all very well, but actually the blob of paint isn't running along, isn't staying in that same circular path, it's going to be moving along. So we're going to need a slightly different approach in finding the position of the blob of paint. Okay, let's think about the horizontal position of the blob of paint. So at the moment you can see here it starts at the x value here. Let me just drop a dotted line down there. That x value there that it starts at is actually given by r cos theta. Just dealing with taking that little right angled triangle there, you can see here that the x position initially is going to be r cos theta. So I'm going to make that the starting point for our blob of paint. It's going to start with x position r cos theta. And I hope you can see then that in the vertical direction its initial position is going to be r, this vertical dotted line here is length r, and then plus, if you consider that right angled triangle there, that little height there, that extra bit is r sine theta. So the vertical position of our blob of paint is initially going to be r plus r sine theta. Now the y direction is actually slightly simpler than the x direction, because the y direction is always related back to this same horizontal line. This horizontal line here is y equals r, and that as the blob of paint turns, sine theta will change, and it will always tell us how far above or below that line the blob of yellow paint is. So we have our position for in the vertical direction in terms of theta. So we have our y component of our parametric equations. I hope you can see where this is going. Now the x one is slightly trickier because the x direction is going to change as the tyre rolls along. The horizontal is going to change a bit more in a slightly more complex way. And we said at the start that the blob of paint is going to mark the ground at circumference length intervals. So the horizontal position of the blob of white paint is going to depend on how far round the circle has turned. So what I want you to think about is just look at this little section of tyre here. Okay, imagine as the tyre rolls along, as that section of the tyre is traced out onto the ground here, can you imagine the centre of the tyre is going to move along by the same horizontal distance? Now using radians, if you know that theta is given in radians, you know that that distance there, let's call it s, you know that that arc length there is given by r theta. That's a little C1 or C2 method. So s equals r theta. And that means that the position of the horizontal position of our blob of paint is going to be r cos theta minus however far the centre of the circle has moved back along the x-axis, so minus r theta, minus the length of arc that's been kind of traced out onto the road as you go along. And that gives us our parametric equations for the path of the blob of paint. Now this path is actually incredibly difficult to work out in Cartesian terms, so it was quite tricky to work out our circle equation, but if we move our circle along, the Cartesian equation becomes very complex. But you can see here using parametric equations, so bringing in this extra parameter of theta actually makes these equations reasonably simple to work with, and we can work in a minute. We're going to have a little look at how to differentiate those so we can find the gradient of that graph. If you plot these equations onto a graphing package, you end up with a graph that looks like this, and you can see here my dot of white paint starts over here, and as the tyre turns, as the wheel rolls along the ground, you can see here the path that the dot of white paint traces out. And here I've extended it so you can see that each circumference that the wheel rolls through produces one point where the white paint just touches the road and makes that little dot that we were expecting as we go along. Okay, so let's take a look at differentiating parametric functions. Differentiation for the parametric function is based on the chain rule idea, and you can see here that I've expressed this as dy by dx is dy by dt times dt by dx, but actually more commonly we use this version, dy dx divided by, sorry, dy dt divided by dx by dt is a more common way of working out a parametric derivative. Okay, so we're given here our curve. This is very similar to the function that we were just looking at. Wouldn't produce exactly the same shape, but something similar to that. So we have x is 4 plus 2 cos theta, y is 2 plus 2 sine theta. Theta is our parameter. Okay, remember theta is variable, so we need to account for it when we differentiate. Let's work through then. Dy by dx is going to be dy by dt divided by, I'm actually going to change that t to theta, sorry, dy d theta divided by dx d theta. Okay, dy d theta then, we're differentiating 2 plus 2 sine theta, the 2 disappears, and the 2 sine theta becomes 2 cosine theta. We're differentiating with respect to theta here, so there's no need to put d theta dx or anything else complicated on the end there, just straightforward 2 cos theta. If we differentiate x then with respect to theta, the 4 disappears and we end up with minus 2 sine theta in the denominator there. We can do a little simplifying, cancel through by 2, and we've got negative cos theta over sine theta, which I hope you're familiar with as being negative cot theta, which is our answer B here. Okay, now we're looking at functions relating to x, y and t. T is our extra parameter in here. We're looking for the coordinates of the turning points of this particular curve, so we're looking for where dy by dx, the gradient function, equals 0. Okay, so differentiating y with respect to t first of all gives me 3t squared minus 2t, and differentiating x with respect to t underneath gives me 2. So we're looking for where 3t squared minus 2t over 2 equals 0. If we multiply it by 2, that disappears again. We can factorise. I think we can take out a factor of t. So 3t minus 2 is 0. That means that at the turning points t equals 0 or t equals 2/3. So I'm going to guess that this particular set of coordinates here belong to t equals 0, but let's just check that. When t equals 0, x is equal to 2t minus 3, so 2 times 0 minus 3, that gives me my minus 3, and y equals 0. Okay, so we're not interested in this one, that's been used already. Okay, so we'll ignore that one. Let's take t equals 2/3 then. When t equals 2/3, x is going to be 2 lots of 2/3 minus 3, which is 4/3 minus 3, which I make 4/3 minus 9 over 3, which I think is minus 5 over 3. And y is going to be equal to, that means we can eliminate a couple of answers already, doesn't it? We can get rid of those two. Y is going to be t cubed minus t squared, which is going to be 8 over 27 minus 4 over 9. If we turn it all into 27ths, that's 8 minus 12, which I make minus 4 over 27. So our second set of turning points there, minus 5 over 3 and minus 4 over 27, which I think is answer D. Okay, so that brings us to the end of our session on implicit differentiation and parametric differentiation. I hope you found that useful. If you're interested in further online or face-to-face revision events or any of the other activities that the FMSP is involved in, please do go to our home site at www.furthermaths.org.uk. I hope you find that useful and hope to work with you again. Thank you and goodbye.